In this video, we're going to look at finding the equation of a regression line. You might have done some work with scatter graphs or scatter plots in the past. So we can see this one looks to be fairly strong positive correlation. So we've got X and we've got Y. This one looks to be perfect or near perfect positive correlation. They're all in a straight line. This one looks to be fairly strong negative correlation, and this looks to be near perfect, if not perfect negative correlation. This one right here, we could say there's no linear correlation. That doesn't mean that there's no relationship between X and Y, it just means that it's not a linear relationship. We might have been asked to put a line of best fit on these. So we would do this by eye. And if I had my line of best fit, the idea is we have roughly the same amount of points either side of the line. So this one would look something like so. This one looks like it's going to go absolutely perfectly through these. So this looks to be positive and it's going to be near perfect, if not perfect correlation. If we look at this one right here, again, by eye, we can see it's going to be approximately there, and then this one looks to be bang on that line. Quite clearly, we wouldn't look to apply a line of best fit to this one right here, as there's no linear correlation. I've done this by eye. There must be a better way in which we can find now a line of best fit. And that is simply by finding what we call the regression line, or the line of least squares. When we have a regression line, it allows us to make estimations or predictions of values of one variable in response to another. So let's look at the idea of an explanatory and response variable. You might hear explanatory called now the independent and the response the dependent. So if you've done any work with functions before, let's say now y is a function of x. So y is equal to the f of x. So we might say now the f of x is going to be equal to 2x plus 1. So I can see now that my independent variable x is going to now take a certain value. So it might take anything from negative infinity to positive infinity. It might take all real values. We might put something in. So if I wanted to do f of 1, we would have now two lots of 1 plus 1. So we could say that the f of 1 was equal to 3. So we can see from this y is equal to 3. This now is the dependent variable. This is the independent variable, this is the dependent. With our scatter plots, we get something very similar. We have what we call the explanatory, which is now the independent, and then the response, which is the dependent. So for example, now if we had temperature, let's say we had temperature. So if we thought about temperature and ice cream sales, as the temperature increases, the ice cream sales increase. So it's a cause and effect. The more the temperature goes up, the more ice cream sales goes up. And we represent now the explanatory variable on the x-axis and the response on the y. So with our line of best fit, or our regression line, we can now look at making estimations and predictions given certain values. Okay, let's look at this idea of the line of regression, or the least squares line. And what I'm going to do is just draw something up. So what we're going to have then, if we have the axis like here, we're going to have lots now of, let's just put loads of dots on here. So let's go ahead and put some dots on here. This is looking to be now positive correlation. So what we're going to have some dots here, okay? And then we'll have something that looks a bit like this. So if I now put on a line of best fit, now this line of best fit is going to go through what we call x bar, y bar. So if this is y now, what we'll have is the mean of y and the mean of x, and it will go through that point. So let's go ahead and put that on. So if we put that point, let's say that that's going to be here, and let's say that's x bar, y bar. What we're looking to do now is find a line of best fit, and we're going to work out quite a technical way of finding this. So it's going to go through the mean. So the mean of these two, and let's see if we can get that looking a bit. Let's see if we can put that on. And that might be just there. So let's put that there. That's not accurate, but it'll give you some idea. So this is what we call x bar, y bar. It's the mean of both. What we're looking to do is essentially move this line around such that the distances between the points from the line, so the observed values from the line, are as small as possible. Now you can see we've got some above the line and some below the line. If we just took the value of these, we would end up with some positive and some negative. So what we do to get around this is take the square of each. Now, if I draw these on, let's go ahead and get some squares. So let's put that one just there. Let's put that square just there. And I'll start putting these on. So what we're going to see, and let's put this one just here. Let's do that. Now, these, as you can see, are not squares. It will all depend on the scale that you have of these. But essentially what we're doing now is building up these little squares. What we're trying to do is minimize now the area. We're looking to reduce now the total sum now of these squares. And the reason we're using squares is such that we don't have these negative values. So essentially this is the absolute value. So what we'd have, let's do another one of these. Now the more I move this around, the more I can either increase the sum of all what we call the residuals. The residual is essentially, now let's put this on, the residual is this distance between now these observed values and the line. So let's put that one on like so. So this is what we're doing. Now there'll come a point where these become as small as possible, and that's the idea of the least squares line, such that we can minimize the area of these. And as you can see, these are quite pretty, and over time we're going to have all of these. So the more we can reduce this, the better the line of best fit is, and the more accurate it is. We call this now the regression line, and we say this is the regression line of y on x. So in this particular case, we've got y on x. If we had, for example, s and t, it would now be s on t. And in later videos, we'll look at some of the technicalities of that. Now, any work you've done before, you know that an equation of a line can be put in the form y is equal to a plus bx. Now, you might have seen it along the lines of y is equal to mx plus c. Let's just put, rather than m is equal to mx plus c, y is equal to mx plus c. What we're going to do is just, let's see that. So this is the form that you've probably seen it in. Of course, it could be written in this form right here. What we're going to do is look at calculating now the least squares line, or the line of regression. It's quite formulaic, and you will be given this now in any particular exam that you're going to sit. What we can say is the following. We can say now, in this particular case, this is the equation now of this line right here. We can say that a is equal to y bar, which is the mean of y, minus b multiplied by x bar, where x bar is the mean of the x values. Okay, let's now look at b. b is going to be now sxy, and this is a quantity we've met before, divided by sxx, and again this is a quantity we've met before. This now sxy is saying if I have sxy, I've got the sum of xy minus the sum of x multiplied by the sum of y over n, where n is the number of items that we've got. So we've got this right here. We've got the sum of x, the sum of y, and then we're subtracting away. So let's just write this. This is sxy. If you like, you could write that this was going to be now the sum, and you can have x minus x bar multiplied by y minus y bar. Or you might see x1, or xi I should say, and then yi. More likely though, you will be working with this particular format. So that's sxy. Let's look at sxx. Essentially this now is n multiplied by the variance. So we have the sum of x squared minus the sum of x all squared over n. So if you haven't seen variance before, then do have a look at that. But these are these two quantities that we're going to compute that will give us now this line of least squares, or the regression line, or if you like, if you want to think about it, a very good line of best fit. Doing it by hand is quite clearly not going to be the best option, knowing that we can calculate it. And we can calculate it simply by using these. So what we can say then is the following. Y is going to be equal to a plus bx. So we've got now that we're going to sub these in. So a is this value right here, and b is this one right here. So let's go ahead and have a go at this, and we'll just make up some data and work through an example of it. Let's take the scenario where we've got now a regional manager of some leisure centres, and he's got a range of leisure centres. And what we're going to do is look now at the number of football pitches and then the games of football that are played in a day. So let's build up some values. So what we're going to have then is x. We'll let x be equal now to, and I'll write it here, x is going to be equal to the number of pitches. Okay, so the number of pitches at any one of these leisure centres. Y is going to be the number of games played. Okay, so let's put this in. So if we look at this now, we can see that the explanatory variable is going to be x and the response variable is going to be y. So if we plotted this, x along the bottom is the number of pitches, and now the response is the number of games. Does that say placed? It should be played. Okay, so let's plug in some values. Let's make this nice and easy. So let's go along the top. Let's say we're going to have, let's say we've got 2 pitches. Let's say we've got 4. Let's say we've got 3. Let's say we've got 7, and let's say we've got 6. So in this initial example, we will keep the numbers down. Now, when you're working with this data, in some questions, you'll be given the summary statistics. So you'll be given now the sum of x squared, or you might be given some other values, and you can calculate this. What we're going to do in this video is essentially work from scratch and just go through an example. Okay, let's give these some values. Let's say that 8 games were played at that one, 12 at that one, 10 at that one, 20, let's go for 20 here, and let's go for 15. So nice numbers that I can square. So what we're looking for then now is a. So we can put this in the form y is equal to a plus bx. Okay. Now, if I want to work this out, I can say that a is going to be y bar minus b x bar, where b is given to be sxy over sxx. So let's first work out sxx and sxy. So sxx is going to now be the sum of x squared minus the sum, let's just make that look a bit neater. That's going to be now the sum of x squared, let's write this in, the sum of x squared over a. So let's plug some numbers in. We need first the sum of x squared. So let's just put above here x squared. So that's going to be 4, that'll be 16, that'll be 9, that'll be 49, and this is going to be 36. So let's go ahead and add those up. So we've got sxx, and that's going to be the sum of these right here. So that's 20, that's going to give me 29, and then what are we going to have on that? That's going to give me 78, and then we're going to have now 100, and what's that going to give me? 114. So that's going to give me 114. Let's check that, 114. Right, so that's going to be the sum of x squared, so 114. So all I've done now is sum the x squared. Minus now the sum of x. So if we add these up, so that's going to be 6, then we're going to get 9, we're going to get 16, and then we're going to get 22. So that's going to be 22 squared over the number of data items that we got, which is going to be 5. Okay, so that's sxx. So let's just calculate sxx. So we've got now, we'll grab a calculator for this, we've got 114, and then we're going to minus now 22 squared over 5. And that's going to give me now 86 over 5. So that's 86 over 5. Now, it's good, I think, to get into a habit of just storing this in the calculator. That's a nice number to work with in comparison to what you might get. So shift store, now I'm going to store this in as A. So let's just do that. Let's shift store A. So that's in as my answer A. So if I wanted to come back to that, all I'd do is hit that, recall A. Now, quite clearly with this one, we didn't really need to use it. But again, the level of accuracy is really quite important. So if you're dealing with horrible numbers, whack it into the calculator, store it. Okay, let's look at sxy. Sxy is going to be the sum now of xy. Now, the sum of xy is going to be the multiple of these two, okay? And then what we're going to have is minus the sum of x multiplied by the sum of y divided by n. So let's multiply these. What's that going to give me? That's going, and I'll just put these straight through the calculator to save me the hassle. If I multiply those two, I'm going to get 16, then I'm going to get plus 48, plus 30, plus 140, let's put that in, plus now, that's going to give me 90. So what's that going to give me in total? That's going to give me 324. So what we've got then is sxy. Sxy will be equal to 324. Now what I need to do is multiply the sum of x by the sum of y. We already know the sum of x as we work that out. But if we work out the sum of y, that's 20, 30, then we're going to have 50, so that's going to be 65. So we've got 22, which is the sum of x, multiplied by 65, which is the sum of y, and we're going to divide that by 5. Okay, that's 5 is just the number of data items. So let's go and do that. Let's put that in here and we'll store that in. So we're going to subtract away from this now 22 times by 65 divided by 5. I suppose you could tie that up and just do 22 times 13 if you wish, but again, don't lose marks just to do that. So that's going to be 38, which works out really quite nice, doesn't it? So let's store that in. So we can say that SXY is equal to 38. And I'm going to say that's B. Again, don't need to store a value like 38 in, but if it's 38.674 and so on and so forth, store it in. So shift store B, and that's in as B. So that's now B. Okay. So what we've got then is the following. We found B. Now B can be given as SXY over SXX. So B is going to be now my 38 over 86 over 5. So let's go ahead and do that. Let's just now divide that. And remember, A is stored in the calculator. So if you want to do this, you can just put that value in. So that's going to give us 95 over 43. So B is equal to 95 over 43. So let's go ahead and put that there. So let's do that, 95 over 43. Right, okay, so that's B. So we worked out B. Now let's look at A. That's B, we need A. A is given to be y bar minus B x bar. Now we've already got B, so we can sub that in. Let's look at y bar. Y bar is going to be all of these values divided by 5. And you can see that y bar is just simply the 65 over 5. So we can say that A is going to be equal to now 65 over 5, which is going to give me now 13. 65 over 5 is 13. And then we're going to have minus now the 38 over 5 over 5. So if we just think about that now, that's going to be x bar. So x bar was given now as this value right here. So x bar, my apologies, what's x bar going to be? Let's just add that up. We've got 22. So x bar is going to be 6, 9. Then we've got now the 22. So 22 divided by 5. So 22 divided by 5. And that now is my my value of x bar. So let's go ahead and do that. So let's do that. So let's put in. So now what we've got then is B, which is going to be the 95 over 43, and then multiplied by our value of x bar, which is 22 over 5. So that's what we've got. So let's now work out the value of A. So if I now multiply this, let's multiply this. And I'm just thinking I'm being just a little scrappy with my workings, but hopefully you're following and you have some idea of where it's going. So let's do 13 minus this answer. And that gives me now the 141 over 43. So what we've got then is the following. So we've got A is equal to 1, and what was it? 141 over 43. So we can now put this back together and say that the least squares line, or the regression line, or the line of best fit is given as y is equal to A plus bx. So y is given as 141 over 43, and then we're going to have plus now 95 over 43x. And I suppose if you wanted to tidy that up, you could write it as y is equal to 1 over 43. Let's write that there. Then we'd have 141 plus now 95x. And that would give us now the equation that we're looking for. So if you think about that now, let's just think about what that's going to look like if we had that. So let's have this scenario. We're going to have now the y-intercept just here, 141 over 43, which is going to give us, give or take, about 3.5. Let's look at that. About 3.5, let's say, roughly. I'm kind of working off the top of my head. Let's see what it is. 141 divided by 43. Later on, we will look at the interpretation of this, so 3.27. And then the gradient is, let's 95 over 43. It's going to look something like that, which is about 2.2. So we're going to have something that does this, and we could just label this up. So now this is going to be the regression line, or the line of least squares. So what we've got then is y is equal to 141 over 43 plus 95 over 43x. So we could say this was now y on x. It's the regression line, y on x. So that's how we've done it. And again, if you plotted this data, then you would see how that fits relative to it. So all we've done is taken this and used these basic calculations that we've met before that are in the formula book to work that out. As stated, in a later video, we'll look at some of the subtleties of this and look at some coding. But for now, I just want to get some sense of what we're doing to calculate this. In terms of the jump between the two, this is quite sort of it makes sense, and then we go straight into these formulae or the equation of it that finds it, and there seems to be a gap. The actual proof of this, or showing how it works between these two steps, is kind of a bit beyond the scope of the course, but essentially some idea that you're looking to minimise what we call these residuals. The residual is the difference between here, and we've squared them such that we don't get these negative values. At least gives you some idea of what's going on. Earlier on in the video, I said that we use this line to make estimations and predictions. So if we consider an estimation, say I've got some value of x here, I can go up to that line and now look at the response variable y and make an estimation. What I want to now consider is making predictions, and this is really quite important. We have two scenarios, interpolation and extrapolation. Now, interpolation considers the data values within the range that we've got. So, for example, now, if we look at this right here, the range that we've got of x, these are now going to be the number of pitches at these given leisure centres. So if I thought about wondering how many games are played at 5, this is a poor example because quite clearly, you know, there's very few values and it's not ideal. But, and of course, these are discrete pieces of data, but if I wanted to find 5, I could make a pretty good approximation, and that's called interpolation. So we're using values within our data range to look to make now an estimation. Now, if we think about taking a value outside the data set and making a prediction, whilst this can be quite beneficial, it does have some potential limitations, and we have to treat extrapolation with absolute massive caution. Now, if you think about an example, let's make some examples. Let's say now the following. Let's say we had we started off now. Let's draw a line of best fit. In fact, we'll draw some points. What I'm going to do is boil a kettle. So this is going to be now t. This is going to be the time, and this will be t seconds. Okay, let's say that's t seconds, and let's say this is the temp, and I'll call this capital, and we'll say that this is going to be degrees C. Now, straight off, we're going to start with the water temperature being something, so it will look something like this, and then we'll have something, and it will be getting bigger and bigger and bigger, like so, and then it will start to boil. Now, it would be fair to believe now at this stage I could put through here a line of best fit, and that looks pretty good. So what we could do is say, well, if at this point, let's just do a read-in. Let's go from here. Let's grab that one. In fact, let's say we wanted a read-in. Let's say this was after 1.5 minutes and 90 seconds. We could get that, and then we could get that one, and we could get that one, and we would be interpolating. We're looking at values within the particular data range, and that's fine. You know, whilst it's an estimate, it's a pretty good estimate. But if you consider now boiling a kettle, what's going to happen is going to do this. It's going to get very hot, and then all of a sudden, we're going to, and these are pretty poor crosses, but hopefully you can see what's going to happen. It's going to boil, it's going to hit this level, then later on, what's going to happen is, it's going to go back down to room temperature. Now, if I extrapolate, i.e. I take, say, let's just say this is 90 seconds. Let's say I wanted to think, well, 90 seconds it's going to be at the temperature. I don't know what a kettle's going to be at that temperature. I don't know, let's say it's 60 degrees C. It's probably a little conservative. Now, if it's there, what I'm saying is it's going to follow this linear pattern. So if I now think, well, where's it going to be after 180 seconds, it would seem logical that this line, we can follow this up and now make a prediction. Now, we know quite clearly that that's not going to be any good. So if we are extrapolating, we need to be absolutely 100% in the understanding this has to be treated with caution. And again, this just shows why. Because these, whilst we've got now a linear relationship within the data set, it's not always going to be linear, especially if you're working in the real world. So just be aware. Interpolating within the data set, it's fair to do that. Extrapolating, you need to treat it with some caution. So there we go, basic introduction now to the equation of a regression line, or the least squares line, or if you like, the line of best fit. In later videos we'll take this on and look at this in context and look at some more of the subtleties in how to read and interpret given situations. But hopefully for now, that's given you enough information to start with. Essentially what you've got, if you simply want to plug this in now to the the formula for the equation of y on x is going to be y is equal to a plus bx, where a is y bar minus bx bar, and b is calculated as sxy over sxx. You simply use exactly the same techniques that you would have done when you're looking at other topics. So when you've met this before, for example, in correlation, you would have used exactly these same values, plug them in, and that will give you your line.